We have three main types of collisions in one dimension. The first type is the inelastic collision, like the bat and the golf ball or a baseball. This is an inelastic collision. In such a collision, the ball will be deformed during the action time. Then the restoring force will restore the ball to its original shape as it leaves the bat. For this collision and all other collisions, momentum is conserved, but kinetic energy is not. Kinetic energy in inelastic collisions is not conserved. The second type of collisions is perfectly inelastic collision. In this case, the two objects collide and stick together, like when you throw a dough to some other object, it will stick to it. That would be a perfectly inelastic collision. Again, momentum is conserved and kinetic energy is not conserved. The third type of collision is the elastic collision, like the collision between billiard balls. In this collision, both momentum and kinetic energy are conserved. So momentum before collision equals momentum after collision, and kinetic energy before collision equals kinetic energy after collision. This is a summary of the three types of collisions. As you can see, momentum is always conserved. Kinetic energy is conserved only in elastic collisions. A car and a large truck traveling at the same speed collide head-on and stick together. This means this is a perfect inelastic collision. Which vehicle undergoes the larger change in the magnitude of its momentum? You need to apply the conservation of momentum principle, right? When you do that, you know that the change in magnitude of momentum is the same for both. This is a graphical representation for perfectly inelastic collision. So before collision, you have two objects moving toward each other, M1 with V1 initial, M2 with V2 initial. After collision, they stick together. So now the new system after collision is a system of a new mass, M1 plus M2, moving with a new velocity V final. So you need to conserve momentum, M1 V1 initial plus M2 V2 initials, vector addition is equal to M1 plus M2 V final. This is how we conserve the momentum. Okay, so now you can solve for V final. V final equals M1 V1 initial plus M2 V2 initial divided by M1 plus M2. So now you can calculate the velocity of the new system. This is a nice example that I selected for discussion, where we make use of the perfect inelastic collision. The ballistic pendulum. This device is used to measure the speed of bullets, fast-moving objects. So the bullet is fired, interested in measuring the velocity. We have no direct method to measure the velocity, but we use this trick to measure the velocity indirectly. So as the bullet hits this wooden block, because of the momentum, because of conservation of momentum, the block will move with some velocity. As it moves, it will swing. So here you have like a pendulum. It will swing to some height. When it reaches maximum height, it would have moved up a distance h. As we learned from chapter 5, conservation of energy principle, at this point the energy was all kinetic. At maximum height, the energy is all potential. It's easy to calculate the potential energy. Mass m1 plus m2, G 9.8 multiplied by H. That is the potential energy at maximum height. And that is equal to the kinetic energy, which is m1 plus m2 multiplied by v squared for this system, divided by 2. Half mass by v squared, that would be kinetic energy. It's easy to measure the masses, it's easy to measure the height, so it's easy to measure, applying the conservation of energy principle, it's easy to measure V for this system, and then we apply the conservation of momentum principle, and we can solve for the initial velocity of the bullet. As an example of this technique, assume the mass of the bullet is 5 grams and the mass of the pendulum is 1 kilogram and the height is 5 centimeters. Now calculate the velocity of the system after the bullet and after the bullet embeds in the block, and calculate the initial speed of the bullet. So from the conservation of energy, the potential energy m1 plus m2 GH equals the kinetic energy for the block and the bullet, half m1 plus m2 v squared. So we divide by the masses, m1 plus m2, both sides. We end up with this simple equation. V squared is equal to 2 multiplied by GH. V is square root of 2GH. 2 multiplied by G multiplied by H. We have to change from centimeter into meter. So now we know the velocity for the system. That includes the block and the bullet. Okay, 0.99 meter per second. Then from the conservation of momentum, we know that initial momentum equals final momentum. Initial momentum, we have m1 v1 initial. That was at rest initially, doesn't have momentum. After collision, we have m1 plus m2 moving with the velocity of the system. Okay, so now we can solve for v1 because v2 initial is 0. So this equation eventually is m1 v1 initial equals m1 plus m2 v system. So you can solve for v1 initial. It is m1 plus m2 v system divided by m1. We substitute for the masses. m1 plus m2 is 1.05 kilogram. V system is 0.99. And m for the bullet, 5 grams, means 5 by 10 to the minus 3 kilogram. Solve, evaluate, the answer is 199 meter per second. That would be the velocity of the bullet. This is a nice example where we make use of what we learned concerning energy and concerning momentum. An object of mass m moves to the right with a speed v. It collides head-on with an object of mass 3m moving with a speed 1/3 v in the opposite direction. If the two objects stick together, what is the speed of the combined object of mass for m after the collision? So to solve this problem, you need to conserve momentum. Before collision, you are talking about two objects, one with mass m and velocity v, so the momentum is mv. The other with mass 3m and velocity v over 3, so the momentum again is mv. This is moving to the right, the other moving to the left, so the momentum before collision was 0. mv minus mv is 0. Therefore, after collision, the momentum must also be 0. For elastic collisions, in general, before the collision, you may have this situation. M1 V1 initial, M2 V2 initial, and after the collision, V1 may bounce back, V2 bounce back, because M1 is smaller in mass, the velocity will be greater. And because M2 is heavier, its velocity will be smaller. Remember, we are conserving momentum. The product of mass by velocity is the conserved quantity. So here, when we apply the conservation of momentum, you have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Because it's elastic collision, so kinetic energy is also conserved. So we have a second equation, half M1 V1 initial squared plus half M2 V2 initial squared equals half M1 V1 final squared plus half M2 V2 final squared. So we have two equations rather than one, which means we can use them to solve for two unknowns. As you know from algebra, the number of unknowns is equal to the number of simultaneous equations. We can simplify these equations, and with further simplification, if the masses are identical, you can divide by the masses and you end up with this result for the change in the momentum, the change in the velocities. So V1 initial minus V2 initials equals minus V1 final minus V2 final, because they are in opposite direction. When you solve collision problems, you need to sketch the problem to define the coordinates, to determine directions. Then you will apply the conservation of momentum, momentum before equals momentum after. And if the collision is elastic, you can also write an equation for the kinetic energy. And then you just apply algebra and solve for the unknown quantities. I selected this example for elastic collisions. Two billiard balls of identical mass move toward each other as in the figure, with positive x-axis to the right. Assume that collision between them is perfectly elastic. If the initial velocities of the balls are 30 and 20 centimeters, what are the velocities of the balls after the collision? Assume friction and rotation are unimportant. So this is before collision, this is after collision. You apply the conservation of momentum principle. Since the masses are identical, you can divide by m all terms. You end up with this equation for the initial momentum, 30 plus minus 20, because it's in the opposite direction, equals V1 final plus V2 final. Okay, and because it's elastic, from the conservation of energy, we have this result that we obtained from the previous discussion here. This equation that we can also make use of. So now you have two equations with two unknowns that you apply algebra and solve for the two unknowns. So V2 final is 30, V1 final is minus 20. Okay,